Hi everyone, welcome back to this video series on data centers. The data link layer. The data link layer provides the physical transmission of the data and handles error notification, network topology and flow control. This means that the data link layer will ensure that messages are delivered to the proper device on a LAN using hardware addresses and will translate messages from the network layer into bits for the physical layer to transmit. The data link layer formats the messages into pieces, each called a data frame, and adds a customized header containing the hardware destination and source address. This added information forms a sort of capsule that surrounds the original message in much the same way that engines, navigation devices and other tools were attached to the lunar modules of the Apollo project. These various pieces of equipment were useful only during certain stages of space flight and were stripped off the module and discarded with their designated when their designated stage was complete. Data traveling through networks is similar. Figure 215 shows the data link layer with the Ethernet and IEEE specifications. When you check it out, notice that the IEEE 802.2 standard is used in conjunction with and adds functionality to the other IEEE standards. It's important for you to understand that routers which work at the network layer don't care at all about where a particular host is located. They're only concerned about where networks are located and the best way to reach them, including remote ones. Routers are totally obsessive when it comes to networks, and for once this is a good thing. If the data link layer that's responsible for the actual unique identification of each device that resides on a local network for a host to send packets to individual hosts on a local network, as well as transmit packets between routers, the data link layer uses hardware addressing. Each time a packet is sent between routers, it's framed with control information at the data link layer, but that information is stripped off at the receiving router and only the original packet is left completely intact. This framing of the packet continues for each hop until the packet is finally delivered to the correct receiving host. It's really important to understand that the packet itself is never altered along the route. It's only encapsulated with the type of control information required for it to be properly passed on to different media types. The IEEE data link layer has two sub-layers. Media Access Control MAC 802.3 defines how packets are placed on the media contention. Media access is first come, first served access, where everyone shares the same bandwidth, hence the name. Physical addressing is defined here, as well as logical topologies. What's a logical topology? It's the signal path through a physical topology. Line discipline, error notification, not correction, ordered delivery of frames, and optional flow control can also be used at this sublayer. Logical link control, LLC 802.2, responsible for identifying network layer protocols and then encapsulating them. All LLC header tells the data link layer what to do with a packet once a frame is received. It works like this. A host will receive a frame and look in the LLC header to find out where the packet is destined, say the IP protocol at the network layer. The LLC can also provide flow control and sequencing of control bits. Switches and bridges at the data link layer. Layer 2 switching is considered hardware based bridging because it uses specialized hardware called an application specific integrated ASIC. ASICs can run up to gigabit speeds with very low latency rates. Bridges and switches reach each frame as it passes through the network. The layer 2 device then puts the source address in a filter table and keeps track of which port the frame was received on. This information logged in the bridges or switches filter table is what helps the machine determine the location of the specific sending device. Figure 2.16 shows a switch in an internetwork. The real estate business is all about location, 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 and it's the same way for both layer 2 and layer 3 devices, though both need to be able to negotiate the network. It's crucial to remember that they're connected with very different parts to it. Primarily, layer 3 machines such as routers need to locate specific networks, whereas layer 2 machines, switches and bridges need to eventually locate specific devices. So networks are to routers as individual devices are to switches and bridges, and routing tables that map the internetwork are for routers as filter tables that map individual devices are for switches and bridges. After a filter table is built on the layer 2 device, it'll forward frames only to the segment where the destination hardware address is located. If the destination device is on the same segment as the frame, the layer 2 device will block the frame from going to any other segments. If the destination is on a different segment, the frame can be transmitted only to that segment. This is called transparent bridging. When a switch interface receives a frame with a destination hardware address that isn't found in the device's filter table, it'll forward the frame to all connected segments. If the unknown device that was sent the mystery frame replies to the forwarding action, the switch updates its filter table regarding the device's location, but in the event the destination address of the transmission frame is a broadcast address, the switch will forward all broadcasts to every connected segment by default. All devices that the broadcast is forwarded to are considered to be in the same broadcast domain. This can be a problem. Layer 2 devices propagate layer 2 broadcast storms that choke performance, and only way to stop a broadcast storm from propagating through the internetwork is with a layer 3 device or router. The biggest benefit of using switches instead of hubs in your internetwork is that each port is actually its own collision domain. Conversely, a hub creates one large collision domain, but even armed with a switch, you still don't break up broadcast domains by default. Neither switches nor bridges will do that. They simply forward all broadcasts instead. Another benefit of LAN switching over hub-centered implementation is that each device on every segment plugged into the switch can transmit simultaneously. At least they can, as long as there is only one host on each port and a hub isn't plugged into a switch port. As you might have guessed, hubs only allow one device per network segment to communicate at a time. So here you can see our switch. So there's 3 switches here, and with 2 computers hanging off each. The physical layer. Finally arriving at the bottom, we find the physical layer does 2 things. It sends bits and receives bits. Bits come only in values of 1 or 0. A Morse code with numerical values. The physical layer communicates directly with the various types of actual communication media. Different kinds of media represent these bit values in different ways. Some use audio tones, while others employ state transition changes in voltage from high to low and low to high. Specific protocols are needed for each type of media to describe the proper bit patterns to be used. How data is encoded into media signals and the various qualities of the physical media's attachment interface. The physical layer specifies the electrical, mechanical, procedural and functional requirements for activating, maintaining and deactivating a physical link between end systems. This layer is also where you identify the interface between the data terminal equipment DTE and the data communications equipment DCE. Some old phone company employees still call DCE data circuit termination equipment. The DCE is usually located at the service provider, while the DTE is the attached device. The services available to the DTE are most often accessed via modem or channel service unit, data service unit, CSU, DSU. The physical layers, connectors, and different physical topologies are defined by OSI standards, allowing disparate systems to communicate. The CCNA objectives are interested only in the IEEE Ethernet standards. Hubs at the physical layer. A hub is really a multi-port repeater. A repeater receives a digital signal and re-amplifies or regenerates that signal and then forwards the digital signal out all active ports without looking at any data. An active hub does the same thing. Any digital signal received from a segment or a hub port is regenerated or re-amplified and transmitted out all other ports on the hub. This means all devices plugged into the hub are in the same collision domain as well as in the same broadcast domain. Figure 217 shows a hub in a network. All devices in the same collision domain, all devices in the same broadcast domain, devices share the same bandwidth. Hubs, like repeaters, don't examine any traffic as it enters and is then transmitted out to the other ports of the physical media. Every device connected to the hub or hubs must listen if one device transmits. All physical star network where the hub is a central device and cables extend in all directions out from is a type of topology a hub creates. Visually, the design really does not resemble a star, whereas Ethernet networks run a logical bus topology, meaning that the signal has to run through the network from end to end. Summary. Now you're armed with a ton of fundamental information, you're ready to build upon it and are well on your way to certification. I started out by discussing basic networking and the differences between collision and broadcast domains. I then discussed the OSI model and the 7-layer model used to help application developers design applications that can run on any type of system or network. Each layer has its special jobs and select responsibilities within the model to ensure that solid, effective communications do in fact occur. I provided you with complete details of each layer and discussed how Cisco views the specifications of the OSI model. In addition, each layer in the OSI model specifies different types of devices, and I described these different devices used at each layer. Remember that hubs are physical layer devices and repeat the signal to all segments except the one from which it was received. Switches segment the network using hardware addresses and break up collision domains. Routers break up broadcast domains and collision domains and use logical addressing to send packets through an internetwork. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.